Hey guys, what's going on? So I'm back at it again with this neat code along video series. Today we'll be doing some bug fixes and then implementing the looks of this. So we're gonna try to beautify everything a little bit by adding a trail render and maybe messing with the lights a bit. Uh, One thing I want to say right now, it doesn't really look like what we had in the example scene. One of the reasons is that there's no trail render, but also there's no speciation. The color for each agent comes from the speciation, and I'm just waiting to see how many people actually make it to the end of the series so far. And if more people do, then like if at least like two people comment that they've made it, I'll make the speciation videos next. But so our kind of what's looking like in the future right now for this project is that right now we'll do bug fixes. We'll add the trail render. Then the videos will be the save genome and the load genome. So we want to be able to save and load our genome so that we can visualize it in Python and also be able to load it for future tasks. So we might not always want to have this setup. We might want to take the best trained network from this setup and move it to a different setup where, let's say, the food is moving around, and that way we can really train it better to develop food chasing behavior. But for right now, we just one of the main reasons why we're doing the load and the save is so that we could visualize our genome and make sure that everything is working right. Then after the load and save, we have the speciation. Once that's done, everything is done, color will be in there, and our project will be exactly where our example project is at. So, now moving on, let's fix the the two bugs that are in here right now. So, let's open up our code, specifically open up the neat genome. And you guys can do that by going to your scripts in the editor and just double clicking neat genome. It should open up. But yeah, what the problem is that over here when we do the add random node in the add random node function in our neat genome class, we are adding the first new connection we create, but we're not adding the second new connection. And that's a big problem because whenever the node gets mutated, whenever a new node gets created, that node has no connection to the output side of things. So it has no way to feed its information forward. It's just a floating node, a sinkhole, if you would think about it, for information. So all information will go to that node because it has an input connection, but information can never leave it because it has no output connections until a mutation happens that creates an edge from that node to some other node. Okay, and there's just no reason to have that. The reason why speciation adds this node in the way that it does is so that it has the mutation has a very limited effect on the performance of the network. It gets us ready for increasing our search space, but it doesn't ruin the solution that we've found currently. Now, we can see that because our first node has the value of 1, not our first node. Our first connection has the weight of 1, which means that whatever value is being fed forward to it will remain the same because it's not affecting it at all, right? Anything multiplied by 1 remains that. And then our second node actually has the connection, actually has the weight of our mutating connection. So we're not really disrupting our network at all. Instead, we're just expanding our network. And that's what we want to do, so that we don't lose the solution we worked so hard to get. So let's go ahead and add the second node, which is already created. I just forgot to add it. Now, to do that, we're going to do congenes dot add, because it's a list, and then second new con. And it's as simple as that. Now, our connections are set up. One of the problems, however, is that when we do mutate this connection and we do set it to false, we disable it, but when we create our network, we don't actually check to make sure if a connection is enabled or disabled. We just create it. And that's a big problem, because even our disabled connections are going to be in our network and are actually going to be affecting our feed-forward loop. If they're disabled, they shouldn't even be created in the network, because our genome, our instructions for the network structure, is telling you that this is disabled. This is not a working genome, or not a working gene. So to do that, what we're going to do is, one, we already have it being disabled right here, so that's good. Everything is done for our add random node function. Everything is looking good. But what we want to do to make sure that our network doesn't create disabled edges is go to the network, the neat network script. Go to in the neat network class, go to create network, the create network function, and then in the create network function, here where we do create network edges, we just want to do a check. So we do if congene dot is active equals true, then we want to do that. So basically, if the connection gene is active is true. So if the genes are active, if the connection is active, then we create it. Otherwise, we don't do anything. Now we save that, and everything is looking pretty good for bug fixes. So now that bug fixes are done in our code, let's move back to Unity. And let's, I don't know why Unity in Linux does this weird thing where you see I have a gap right here, but whatever. So what we're now going to do, now that bug fixes are done, and hopefully everything is working right, but before I test it, I want to add the trail renderer. Okay, so we can actually see the path that the agents are traveling. So to add the trail renderer, what we're going to do is go down to the prefabs folder, right? And then we're going to click on the fish prefab, scroll down, add component, and then type in trail right in the search bar and add the trail renderer. Okay? And the trail renderer is really what adds like the pop to this project. This is the visual effects of the project, and this is what brings it closer to what my example project was in the first video. And the settings for this is, I haven't like messed with a trail renderer in a while, but the settings that I like are going to be bringing the width down to like 0.22, 0.23. Okay, adding a like one of these nodes in the at the end, or in the middle, and adding another one at the end. And we'll scroll the one on the right side all the way down. The one in the middle, we'll move that slightly lower, and the one on the right, one on the left is going to be 0.23 or whatever you want it. But somewhere around 0.2 is what I like, because our agents are pretty small, so we want our trail renderer to be pretty thin. And I just like to move this down a little to make a nice curve right here. So now that the width is done, we'll change the time down to like 3. Yeah, and the time is basically how long the trail renderer stays for before it starts fading. So it's like the length of the trail renderer. Okay, and now we'll go to the color. When you click color, you get this nice little gradient editor that comes up, and in the gradient editor you'll see these little like flags on the top right, top left, bottom right, bottom left, right? If you click on the top ones, the top flags, the top ones are actually going to control your alpha. So how transparent you want the beginning and the end of your trail render to be. The left side is the beginning of your trail renderer, the right side is the end of it. So in the beginning, we want our trail renderer to be very very transparent. What's the opposite of transparent? Very non-transparent? Very visible? And then at the end, we want to move our alpha down to 100 so that it's more transparent. So as you go down, the trail will get thinner, like you get more and more see-through. Now we'll change the color of the left side, so the bottom left flag. We'll change that to yellow so that it matches our agent, but not like too yellow, just a nice light yellow. And then we'll change the bottom right flag, so the end of our trail render will be a nice cayenne color. And that's just because I like cayenne. These colors, you guys can do whatever you want. This is the creative side, and I hope you guys do run with this project and do, some cool stuff with it. Cool stuff that makes mine look really crappy, hopefully. So, now, that's looking good. Our color's good. Our time is good. Our width is good. I think the trail render part is done. And yeah, so our bugs are done. Trail render is done. Let's press play, see how it's looking. What? Oh, I know. So the pink in Unity means that there's a problem with the shader, right? And they're right, I forgot to add a shader. Oh no, there's a problem with the material, not a shader, sorry. The pink in Unity means that there's a problem with the material, and I forgot to add a material. Apologies. So we're going to go to the fish prefab again, open the prefab. We're going to scroll down to where we have the trail renderer. We're going to go to the materials part, and it might be closed for you like this. We'll go to materials. You're going to click on this little add button, and what it will do is open the select material menu, or pop-up, whatever. And this is where all your materials are. So you can see the ones that we've made, background, fish, and food. But it also has a bunch of default materials, right? So you have the default particle, which is a nice, the edges are faded out. It looks pretty nice in trail renderers as well. But what we're going to do is use the default sprite. So just click that, X out, and there's your default sprite. So yeah, now it should work just fine. And there we go. We get the nice yellow to cayenne. The transparency is looking decent. The time is not too bad. So it's not too long. And the slower the agents go, the less the trail renderer will be long. And that's a good way to indicate how fast the agents are moving. So you see this one's moving very slow, so its trail renderer is not very long. And that's something I really like about the trail renderers, because it really, in this type of projects, it really gives you a lot of information that you can infer about the agents and how the networks are doing and how the mutations are going. So while I talk a little bit about what's next, I'm just going to move this up to 20 so that you guys can see how this is going. I really wanted to see how our mutation, how our fixes are actually affecting the mutations of this. And if we could get a good agent, really. In the future, we'll do the saving and everything. But for today, for right now, we'll probably just end it here after we see that this is working okay. I really do like the way these look. They're very beautiful. And I'm always mesmerized by the unique behavior you get from neural networks. And really it's just a mathematical function within, it just functions within functions. And in reality, it affects the world in such a beautiful way. It makes you think maybe we are just neural networks, maybe eventually if we find the perfect structure of a neural network, we will get lifelike behavior like us. But, that's thinking ahead in the future. I'm going to move the time up to 30. That is strange though, where we seem to be losing innovation. Like we get networks that are doing okay, but then we lose them. I want to try a couple of things now to optimize a little bit of how our genome is mutating. Let's go back to the code. Let's go to our neat genome. Let's change a couple of these values. What I would like really is more edges and more nodes. But I want to turn down the random weight chance. So we'll change that to like not even 5. We'll change, I mean not even 10. We'll change it to 5. And the true weight chance, we'll change that to like 95. This honestly should be 100. There's no reason not to if your network is not the best network, which we don't mutate, then there's no reason not to perturb. But sometimes you might not want to perturb and just add a node. Who knows? So now that those settings are done, I want to still, let's get out of the prefab of our fish. So by backing out of that. And then now I want to also mess with the neat genome a bit. Because, so we're keeping the best 5, leaving the worst 5. Yet we're losing innovation. Or at least that's what it looks like. The problem with this is there's so much randomness involved, you know, because it's a non-deterministic approach. It's just very difficult to kind of see the patterns in it. Well, what am I even doing? Okay, yeah, I want to make sure that the keep best is working right. So for that, we have to go to the neat G manager, the neat genetic manager. And when we look at the set new population, we have to kind of see what's going on here. We have to also make sure we're sorting beforehand. Yeah, we sort, then we set the new population networks. The new population networks from okay, so for the mutate, we start at the keep best and we go to the end. That's perfect. But when we set new population, we start at 0 and we go to right before our leave worst and we keep those. That makes sense. And then we start at the end of our like we start at where the leave worst would be at. So if we have 20 and our leave worst is 5, we start at 15. And we go to the end. So from 15 to the end, yep, we create our new networks. And then we set our, yeah, everything looks like it's working fine. I wonder why that's happening. Let's try this one more time. We're going to change the speed up to 30. And let's see if we get some good behavior. That agent is not bad. One of the things that might be happening actually, yeah, is that if they spawn close to a wall and if they're not trained very well at avoiding the walls, then they're going to hit that wall. And even if they're really good in the center of the map at finding food, if they're not good at finding the food at the wall, they're going to die and they're going to get lost. Their innovation is going to get lost. So one of the things that might be a good idea is to always spawn them in the same location in the center of the map and see how different networks do. However, that's not a really good solution because in real world cases, that's not how the world works. Now this is an interesting guy, and he got saved. So that means he was, oh, he hit a wall. So he wasn't bad at avoiding walls, so that's why he got saved to the next round. And I'm talking about the guy that was doing some crazy zigzags back and forth and up and down, the agent. But he hit a wall because he was too wild, and that's why he got lost in the innovation. Yeah. And this guy seems to be doing pretty good. Wow, nice. I think there he is again, with a little mutation though. He was like, he saw the guy at the bottom right. He was like, "Oh, I don't want to eat that food," and then he's like, "Oh, I'll eat it." Like, you know, these are just mathematical functions. They're not actual, like, you know, it's not. That's not actually the behavior, but I mean, that's not actually what. I don't know. It's just so weird. What is thinking? What is us? Are we just a mathematical function of signals being fed from our eyes through our brain and to our mouths? So yeah, maybe that is what he's thinking. But it's funny to kind of put human behavior on other natural like behavior, and it makes you think, why do humans kind of have this sight for natural behavior? What do we consider natural behavior compared to like non-natural behavior? It's interesting to think about. So yeah, honestly, we get some really cool behavior, and this is what we were hoping for. This is what I was hoping for when this project was made, and in my other example, there was a problem in that the value of the network was never reset to 0. And now, why does that matter? Because sometimes some values that got fed forward were values that were of previous that because of the way that my implementation is, we're not really setting values. We're feeding to the center and then setting values. So, or the center of each node from their input connections. So in ideal cases, every time the value would just set itself to whatever the new value is. There's no need to set it to 0. But there are some cases where one node would get its value before another node could get set to 0. So it's a gray area of the example. You know, and I just didn't want that. It's cleaner to always, at the end of your feed forward loop, to set your network to 0. To set your values for each node to 0, so that for the next loop, your network is clean. And the only thing that's changing in your neural networks, the only thing that's changing in your neural networks is the weight of the edges. Hey, this guy's doing great. I'm pretty happy with this. I think we'll end it here. This was a really nice talk. This is a really nice code along, actually. It's nice to just watch I always like the ones where I could just watch the training happening and just talk a little bit. So hope you guys enjoyed. If you guys did enjoy, leave a like, do all that. I have 1 subscriber that I'm making these videos for, so I really hope that 1 subscriber enjoys. I do it for you, man. Or girl, I don't know. But if you have any questions, if you need anything, let me know. I hope you're healthy, and yeah, we'll get to the next video. The next video will be on the saving genome and loading genome, Then the videos after that will probably be focused on the speciation, and then there's going to be crossover as well if things go well. Right now, nobody's really made it to the end of this code along, and I don't really think people will right at this point. I'm kind of, on the fence, but I just don't like leaving projects half done, and it felt weird ending where I did, because my example project, it had beautiful trail renderers. And I know it did. It looks nice. And the one where I left off, it looked kind of just like circles chasing after squares. So, I hope you guys enjoy. Leave a like and let me know if you guys have actually made it to the end of this. And I hope to make more videos. Not just on the Neat Code Along, but on a lot of other topics. One of them is actually pretty cool. I hope, and look, you guys can look forward to that. All right, peace out.